Aloha, I'm Jay Barlow, and I'm here today to talk about how variation in acoustic source levels affect density estimation in strange ways, and why mean source levels just aren't good enough. Acoustic point transect abundance estimation depends critically on the area effectively surveyed. Given an estimate of source level, propagation models can be used to estimate detection range, and then a detection range can be used to estimate the area effectively surveyed. For a given number of acoustic detections, the density and abundance are inversely proportional to the area effectively surveyed. However, source level is not a constant. Animal behavior is complex. Animals don't always scream at their maximum volume. Source levels likely vary contextually with different behavioral states, motivational states, animal size, animal depth, energetic state, and breeding season. And variations in source levels are hard to quantify, but as I will show you today, are very important. I'm going to use a Southern Hemisphere baleen whale example here. And fortunately, Brian Miller very recently has used sonobuoys to measure the source level and, importantly, its standard deviation for blue and for fin whales in Antarctic slope waters. The source levels were similar for both species, standard deviations were similar. So I'm going to just generalize that to a baleen whale with a mean source level of 190 dB and a standard deviation of 7 dB. I'm going to use a very simple sound propagation model in some simulations. So I'm just modeling receive level as a function of source level and transmission loss. The detection threshold I'm going to set to 100 dB, re 1 micropascal. And I'm going to assume that animals are detected if the receive level is greater than this detection threshold. Brian and his collaborators modeled transmission loss in their paper and found that it was generally between spherical and cylindrical spreading. So out to 2.5 kilometers, he found that modeled transmission loss was actually less than would be predicted by spherical spreading, which is this dashed dot line. But at ranges greater than, say, 5 kilometers, most of the values fell between the range that you'd expect with cylindrical spreading in a surface duct and spherical spreading, which is this dashed line here. So I'm going to use something intermediate in my models. I'm going to model transmission loss at ranges greater than 2.5 kilometers as 15 log R, 15 times the log base 10 of the range. And at less than 2.5 kilometers, I'm going to assume spherical spreading, as the Miller and his co-authors did. The receive level is shown here for a mean source level of 190 dB. And you can see this receive level crosses the detection threshold right at 74 kilometers. So this model would predict that an animal at less than 74 kilometers would be detected and would not be detected at greater than 74 kilometers. Here you see what the receive levels look like when some noise variation is added to the source level. I assumed a normally distributed source level with a standard deviation of 7 dB. And what you can see is that the receive levels cross the detection threshold at from 5 kilometers to as much as 500 kilometers. This results in a difference in detection area. For this 100-fold difference in detection range, you get a 10,000-fold difference in detection area. And most important, the distribution is not symmetrical around this central value of 74 kilometers. So I estimated what the mean detection range was with and without natural variation in source levels, and I took the ratio of those two. So the mean detection area with variance in source level, normally distributed, over the mean detection area with a constant source level, and that ratio is 6.2. This is a bias. This is an enormous bias in estimating abundance or density. This isn't a 6% bias, this is a 600% bias, a six-fold underestimation of the true abundance if you use the mean detection area. So, as we've shown, using a mean estimate of source level results in an enormous bias in estimates of effective survey area, and consequently in estimates of density and abundance, even with relatively modest levels of natural variation in source level. Well, that's the main point of this entire talk, but it's worth diving a little bit deeper. There are different sources of variation in source level. Natural variation in source level at the animal level, but there can also be measurement error, since these are estimates, propagation error, and localization error in making the source level estimates. The value of standard deviation equals 7 dB from Brian Miller's study includes all three sources of variation shown here. So they're not all natural variation in source level, but that's not the only thing that really matters. Propagation error is also important. So detection area depends on the difference between source level and transmission loss. Error in estimating the transmission loss is relevant, and it's the variance of the difference between source level and transmission loss that biases estimates of detection area, density, and abundance. So if detection loss varies naturally also, that will cause additional bias. There are some solutions to avoid this bias. My favorite, and I think the best solution, is to estimate detection range directly, empirically, rather than relying on propagation models. Available methods include distance sampling, spatially explicit capture-recapture, and trial-based sampling. But there is an alternative. You can use bias correction methods that explicitly consider the natural variation in source level and transmission loss, such as the simulation approach that I used here. What then is needed for these bias correction methods? What we need is more and better estimates of the natural variation in source levels and in transmission loss. We need to be able to partition uncertainty into natural variation and measurement error. Brian Miller and his co-authors were not able to do that, but that's very important in propagating the errors through to uncertainty and estimates of density and abundance. And we need a better understanding of the distributions of this uncertainty, which I'll show here. So knowing the standard deviation of the source level is not enough to specify what the distribution of source levels is. So on the left here, you see source levels that are normally distributed on the dB scale. And on the right, you can see what the distribution of source levels look like if they're normal on the Pascal scale and then transformed back to the dB scale. Both of these plots have the same mean value and the same standard deviation, but you can see their shape is very different. And the bias is very different. As I showed you earlier, the bias, the area bias associated with the distribution that's normal on a dB scale was 6, whereas the area bias is much less if the natural variation in source level is normally distributed on a Pascal scale. And frankly, we don't know how the natural variation is distributed for, I think, any marine mammal. So my take-home messages are that knowing source level and transmission loss is not enough. Knowing the variance and standard deviation of those two is not enough. We also need to know the distribution of variance in source level and transmission loss. Thank you very much.